Welcome to solverfy.
This is the answer to Chapter 19, problem number 59 from the Smith Organic Chemistry textbook. And this problem says, propose a structure for molecule D, which has a formula of C9H9ClO2, consistent with the given spectroscopic data. And then we're given carbon-13 NMR signals, and we're given a proton NMR spectrum. And so we need to use these two types of NMR and this molecular formula to propose a structure. And so, as always in this situation, I think that the place to start is to calculate the hydrogen deficiency index for this molecule. So HDI is going to be equal to 2 times the number of carbons, which is 9, plus 2, minus the number of hydrogens, which is 9, and then minus the number of halogens, which is 1. We have 1 chlorine here. So this comes out, so then all of that is over 2. So this comes out to 20 minus 10, or 10 over 2, which is equal to 5. And so right away, when I see an HDI of 4 or more, I automatically am thinking, okay, well, there's probably an aromatic 6-membered ring in this molecule, because a benzene ring accounts for 4 degrees of unsaturation, 1 for the ring itself, and then 3 for the double bonds inside of the ring. And so we have, in this molecule, I'm going to say a 6-membered aromatic ring, and then 1 more degree of unsaturation. And I see that there are 2 oxygens in this formula. So I'm thinking a carbonyl, and probably, since this is the carboxylic acid chapter, I'm going to go ahead and say we have a carboxylic acid in this molecule. Okay, and so next we have carbon-13 NMR data. And this tells us really only 2 things. So there are 7 signals here, but we have 9 carbons in this molecule. So there are some carbons that are the same, right? So we have 7 signals, but 9 carbons. So we have either 4 carbons that are exactly the same, or no, sorry. So we have 2 pairs of 2 carbons that are equivalent. And the other thing that this NMR tells us is this signal at 179 is pretty far downfield, and that is generally indicative of a carbon-oxygen double bond. Okay, so lastly, we just need to look at the NMR, the proton NMR data, to see what pieces we have and try to put those pieces together. So I'm going to skip to the bottom. This 11.7 singlet is definitely a carboxylic acid. So this tells us that we do, in fact, have a carboxylic acid in this molecule. So there's our 5th degree of unsaturation, and that accounts for 2 of our oxygens. And so I'm actually going to work up here. So the signal immediately above that one at 7.2 ppm is 2 singlets, and it integrates to 4. And so this is in the aromatic proton range, so right around 7. So this is going to be, and I'll just draw an arrow over here, since I'm kind of cramped for space. These are going to be the 4 protons of our aromatic ring. And since there are 4, remember, if there were 6, that would be just a benzene ring. 5 would be a monosubstituted ring, and this is 4. So this is a disubstituted ring. So disubstituted. And so the other thing that we can surmise here is, so in the carbon-13 NMR, we had 7 signals. So as I said, there are going to be 2 pairs of carbons that are equivalent. So this is going to be a para-disubstituted aromatic ring, right? This, or something like this. So here's our aromatic ring. So we're going to have our substituents at the para positions. And we know that because that's going to make these two sets of protons on these carbons equivalent. The two carbons themselves will be equivalent. So not actually those two, though. That was the wrong. So let me switch to red. So it would be more like this. So these two protons and these two protons are going to be equivalent because we will have a line of symmetry through the molecule right there. Okay. So back to the NMR data. We have a 2.6 ppm triplet that integrates to 2. So this is probably a CH2. And then we have a 2.9 ppm triplet that also integrates to 2. So we have two triplets and two CH2 groups. So these are probably splitting each other. And so the one at 2.9 is going to be the one that's connected to our carboxylic acid. And the one at 2.6 is going to be the one that's connected to the ring. And then we have a chlorine to account for. So I'm going to say that this is what we have in this molecule. So here's our chlorine. Then one methylene group, two methylene groups, and our carboxylic acid. And we know that it has to be this sort of structure because the two methylene groups are splitting one another. So it can't be one on one side of the ring and the other on the other. They have to be connected to one another. And there's no other connectivity here that's going to fit with the data that we've been given. So this is the right answer as I've drawn it here. And so again, I think the way to approach this problem, do an HDI from the formula that you're given. Think about what the carbon-13 NMR is telling you, which is that there is a carbonyl, and also that we have two pairs of equivalent carbons. And then just use the proton NMR to get the pieces of this molecule and assemble them in a way that makes sense. And that's the answer to chapter 19.